Assalamu alaikum. From today's lecture, we are going to start the next topic, and this topic is soil compaction. Okay, so the soil is used as a basic construction material. So the soil is a basic construction materials for many projects. Okay, so it could be mostly this soil as a construction material is used in highways, in airports, dams, and also retaining walls. So in case of retaining walls, this is used as a backfill material. Okay, now the advantages of the soil are that soil is available everywhere, it is durable and long lasting, and it is low cost. The only cost is the excavation and transportation of the soil. So in this chapter we are going to look at the property of a soil, which is compaction. So with the help of compaction we are going to improve the soil properties. So mostly if we compare soil with other construction materials, soil is less ideal material. It's not an ideal material, so we have to improve its properties. So the soil is going to be mostly it is weak and it is highly compressible. Compressible means when the load is applied, the soil is going to compress and it is going to settle down. And also the soil has high permeability. Water can pass easily through the soil. So permeability means water can pass through soil. Okay, so that property is called permeability. If permeability is high means the soil water can easily pass, and if permeability is low, then it means water it cannot easily pass through the materials. For example, concrete is not a permeable material. Water cannot pass through the concrete, so it has no permeability. So the problem with the soil is if the soil is weak in strength, it is highly compressible, and it has high permeability. And if we want to use this soil as a construction material, we have to improve its properties. So how can we improve this issue of compressibility? So if the soil is dense, dense soil has high unit weight. So if the soil is dense, it will have high unit weight, and then it will be less compressible. So it is going to be less compressible. Okay, let me write it here. Okay. Okay, so it is going to be less compressible if the density is high. So the purpose of compaction is to increase the density. So the purpose of this process of compaction is to achieve high unit weight. So for that we are going to use a concept which is called stabilization, and the stabilization is a process of improving the properties. So mostly there are two methods of improving the properties of soil. One is called mechanical and the second one is called chemical. So in mechanical we give energy to the soil and we remove the air from the soil and we bring the particles together, we bring particles closer so that it gets into a dense state. So mechanical stabilization is also called compaction. So this is the chapter about. So we are going to discuss this process of compaction in this chapter. So the purpose of this compaction is to increase the unit weight, is to increase the density, okay, to make the soil less compressible. Now mostly in civil engineering, when we are going to use soil, we have to excavate that soil from somewhere. So the soil is going to be brought from somewhere, so we are going to import it from somewhere, and then it means we are going to excavate it. We are going to excavate the soil, we are going to bring to the project area, and then we are going to place it. So in that process the soil is going to be loose, so we have to compact this to a desired density. So what normally we do is we are going to give some energy. Let's say this is our soil in loose state. We give some energy and we bring the particles together, and in this process we are going to add water to the soil. So this water is going to act as a lubricant. It is going to decrease the friction, and particles, these particles can easily slide and they are going to get closer to each other, and the unit weight is going to increase. But when we are going to measure the density, so the density is going to be measured as dry unit weight. Remember, gamma and dry, we never calculate gamma, because if we calculate gamma means it also has the influence of water in it. But when it is gamma d, means it is only the weight of solids over the total volume. So there is no effect of amount of water on gamma d. So in order to measure how good is the compaction, we are going to measure gamma d, and then we are going to compare it with the amount of water. So the purpose of this compaction is to remove the air. So if we look at this loose soil, if this is a loose soil, if this is a loose soil, and soil has three phases: solid, water and air. So in phase in the form of this solid, water and air can be represented as this three-phase diagram. Solid is separated, volume, water is separated, and air is separated. And when the compaction is done, when we give this energy, so when we give the energy, what will happen is that the air is going to go out. So when we compare these two cases, this compacted soil will have no change in the solids. The weight of solid remains same. The amount of water will also remain same, but the amount of air is going to decrease. So the purpose of this compaction is to bring particles together and to expel air from here. So expel or remove air from soil. Okay, so how much energy we need to give, what energy is good for the unit weight, and how much unit weight we can achieve. For that we are going to do one test which is called a compaction test. This test is called, also after the person who developed this test, his name was Proctor. So this is also called Proctor test or compaction test. Okay, before coming to the compaction test, let's look at the advantages of compaction. What is going to happen when we increase the density? Whenever we do the compaction, the unit weight is going to increase. Unit weight So please remember, the unit weight is going to increase. So if the unit weight is going to increase, it is going to increase the strength of the soil. So this is one of the advantage. It will increase the bearing capacity of the soil. So this we are going to study. There is a whole course of foundation engineering. In the course of foundation engineering, you are going to study what is the bearing capacity. At the moment, just remember that it is the load carrying capacity of the soil, how much load we can apply on the soil. So if the soil is dense, it can take more load, it will have more bearing capacity. And when we have applied energy and the soil is compacted, then the chances of settlement is going to decrease. It will have less settlement, and the volume changes are going to be reduced, because whenever water goes into the soil, it is going to swell, and then when water moves out of the soil, it is going to shrink. So that swelling shrinkage is going to reduce. And also the reduction in hydraulic conductivity. This conductivity is also called permeability. So we are going to study this permeability. This is our next chapter, permeability of the soil. So that permeability is going to reduce. When the soil is dense, then water cannot pass easily from the soil. So these are some of the properties that get improved when a soil is compacted. So in here, let's look at general principles. So we add water into the soil and then we compact. So water is going to reduce the friction among the particles. It acts as a lubricant. But if we are going to put too much water, then it is not good. Why? If it is too much water is added, then the soil is going to become too wet, and the water is going to take up spaces between the particles, and the bond will not develop, and the soil density is going to decrease. But if there is too less amount of water, what will happen? Then there is more friction. So it means we need more energy to get the compaction. So we have to give more energy. More energy means more effort. So what we are going to do is we are going to develop a relationship so that we can have a maximum unit weight for a certain amount of water content, and that amount of water content is called optimum water content. This is the amount of water that will give us the maximum dry density. So let me just explain you here how this water is going to affect. So if I plot on the horizontal axis the water content, if we plot water content on horizontal axis, and if we plot the dry unit weight, uh, maybe kilonewton per meter cube or whatever units we are following. So when we keep on adding the water in it, so let's say there's a certain amount of water, certain water content, and we compact to a certain with a standard procedure, so we get this dry unit weight. We add more water and we compact with the same energy. We keep on adding water and then we compact it. So what will happen is that there will be a time when we will attain a maximum density, and after that if we add more water, the density is going to decrease. So this is how the curve looks like. So what happens, the density is going to increase in the beginning. So you see the density is increasing, but after some moisture content, after some value of water content, the density is decreasing. So there is a point where the density is maximum. So this is that water content, this is the water content where the density is maximum, and this is called optimum water content, OPT, optimum water content, and the corresponding density is the maximum dry unit weight. This is going to be maximum. So what is optimum water content? It is the moisture content at which we are going to get the maximum density, maximum unit weight. Okay, so if let's say if this is the optimum water content, so the left side of this curve is called dry of optimum, this side is dry of optimum, and this is the wet of optimum, wet of optimum, dry of optimum. So this side is dry of optimum, the left hand side of the curve is these all values are dry of optimum, and these are all wet of optimum, and this is the optimum water content. So there was a test that was developed by Proctor in 1933, and after the name of this engineer, this test is also called a Proctor test. But there are two tests. One is called the standard Proctor test, and the other one is called modified Proctor test. Standard Proctor test and modified Proctor test. So there is some difference between standard and modified. We will see what is the difference. One is standard test, the other one is modified test. So what we do in this case is we are going to take soil, and then we are going to add water in it. We are going to mix the soil, and after that we will place in this mold. So this is the mold, right? This mold has a standard volume. So mostly there are two kind of molds. One is this 4-inch dia, and the second one is 6-inch dia. 6-inch dia. 4-inch dia or 6-inch dia. So what we are going to do is we are going to place in this mold the soil in different layers, in the number of layers. So mostly in standard test we are going to place it in 3 layers. So first we are going to fill up to a certain depth, and then we are going to apply energy. We are going to compact this layer. So how we are going to compact? So for compaction we use a hammer. So this is that hammer. In this hammer, this is the weight of hammer. This is the weight of hammer. So this hammer is going to be, there are two weights of the hammer. One is for standard test and one is for modified test. So for standard test we use always 5.5 pounds, and for modified it will become double, so it is 10 pounds. So this is 5.5 pounds. So this is 5.5 pounds of the weight. So this weight is lifted. So from here this weight is going to be lifted, and this height is going to be 12 inch. So this weight is lifted by 12 inch and then it is dropped. So when this is lifted and dropped, it is going to put energy and the soil will get compacted. So in one layer we apply this energy 25 times. So we are going to apply this energy 25 times. So this is, let's say, first layer, and we give 25 times energy, and then we are going to compact, we are going to place the second layer, and then it will be compacted, and then we are going to place the third layer, and then it will be compacted 25 times. So it means this soil is placed in 3 layers approximately of same thickness. It is compacted, and after that we are going to do what is the weight of this this whole thing, weight of soil plus mold, and we know the volume of this standard mold. So the volume of this standard mold is 1/30 cubic foot, and if we go in centimeter cube, it is going to be 943 point something. So if we round off, it is approximately equal to 944 cubic, 943 or 944 cubic centimeter. So if we know the weight and if we know the volume, we can easily find out the unit weight. Once we get unit weight, and from moisture content we can calculate the dry unit weight. So this is how this test is done, and when this test is performed, the energy is applied uniformly everywhere in the soil layer. So that energy, I mean, let's suppose there are 25 blows, so this is number 1. So we are going to put our hammer here at number 1, and we give energy, then number 2, 3, 4, 5, 6. Now 7th blow is going to be in the center. So after that, then we are going to start, this one will become 8, then 9, then 10, 11, 12, 13 and 14, and then this is repeated 25 times. When 25 energy blows are given, then next layer is placed, then third layer is placed. So this is how the soil is compacted. So let me show you one video. I took it from the web page of Dr. Kevin Frank. If you are interested, you can go on YouTube and see his channel, and you can see other videos as well. So this is the video about the compaction. So please watch this and note down the important points.
Hello and welcome. In this lab, we will be performing a moisture unit weight relationship, a test better known as a compaction or Proctor test. This is used to determine the relationship between moisture content and dry unit weight. This test covers standards ASTM D698 and AASHTO T99, which are standard proctors, and ASTM D1557 and AASHTO T180, which are modified proctors. We will need the following items to perform this test: all the parts of the compaction mold, a proctor hammer, a number 4 sieve, balance, a pan, straight edge, graduated cylinder, extruder, and an oven. The first thing we need to do is to prepare the soil. Depending on what type of material we are using will determine what we need to do to prepare the soil. There are 3 methods for each type of proctors, i.e. standard and modified. These methods are based on the gradation of the material. Method A, less than 25% is retained on the number 4 screen. Method B, less than 25% is retained on the 3/8 inch screen. And method C, if less than 30% is retained on the 3/4 inch screen. Methods A and B uses a 4-inch mold, and method C uses a 6-inch mold. We will be using a material that is covered under method A. We will screen enough material through a number 4 screen to set up 4 different samples. Seeing how our samples have a significant amount of silts and clays, we will need to soak it for at least 12 hours. Once we have the material screened and separated into 4 samples, we will need to moisture condition the material. To do this, we need to know what the current moisture of the sample is and add the difference of that and the moisture content we want. Unfortunately, it is through experience that we are able to get the moisture samples where we want them. So if you have ever performed this test, do your best. You may end up doing 6+ points to get what you want, or start out too wet and have to dry it all back. Good luck. We will want to change the moisture content of each sample so they are approximately 2 to 3% different from each other. What we are shooting for is to have 2 samples less than optimum moisture content and 2 samples greater than that. For example, if our sample has an optimum moisture content of 12%, we will want our samples at 9, 11, 13, and 15%. The optimal moisture content is when we have enough moisture in the sample to fill all the voids between the grains of soil, but not so much that the water content starts replacing the soil. Once our samples are set up and have hydrated for 12 hours, we are ready to start our test. Since we are doing method A, we will be using a 4-inch mold, and we will be doing a standard proctor, so we will be using a 5.5-pound hammer with 3 lifts and 25 blows per lift. We need to get the weight of the mold without the collar attached before we start our test. The first lift, we will fill the mold up about 1/2 way and compact it. The next lift, we will fill almost to the top of the mold and compact. The last lift, we will fill about halfway up the collar and compact it. When we are done, we want to see the soil at about 1/2 inch to 1 inch above the top of the mold when the collar is removed. At this point, we will use our straight edge to get the soil level with the top of the mold, making sure we fill all the voids. the sample again to get your mold plus soil weight. We will remove the mold from the base and place it in the extruder to remove the soil from the mold. And then break up this sample so we can get a 100 to 200 gram moisture sample out of it. Get the weight on the moisture sample and place it in the oven. Repeat this process 3 more times or more if necessary to finish your curve. You will know you are wetter than the optimum moisture content when your wet soil plus mold weight begins to drop. Let the samples dry overnight, remove and cool to room temperature, and get your dry moisture weight. This will give you all the data you need to calculate and finish this test. That concludes this test. For additional information,
okay, so this was a brief about this test, and this test that you see in this video has to be repeated minimum 4 or 5 times. It depends. So let's look at, suppose we did this test 5 times. So what we are going to do is we are going to make a table we are going to get what is the water content, and then what is the wet unit weight, and then from there we can get what is the dry unit weight. So mostly this test is performed minimum 4 times, or better it is if it is 5 times. So if we and how we are going to get the unit weight, remember the unit weight is going to be the weight over volume, and this mold, as I told you before, that this mold is this mold's volume is 943 cubic centimeter, or 1 by 30 cubic foot. So when the soil is compacted, we know the weight of mold. So if we subtract this weight of mold from that total weight, so it will give us the weight of soil. So from there we are going to get the unit weight, and for moisture content we take from here some soil and we put it in the can, and that can goes into the oven for 24 hours, and next day we are going to wait again, and it will give us the dry weight of the soil plus can, and from there we are going to get the water content. So once the unit weight and water content is determined, the next step is to get the dry unit weight. If you remember, gamma D is gamma over 1 plus W. So we are going to get 5 values of water content and dry unit weight, and then we are going to plot this on this graph. Horizontal axis is water content as a percentage, and the vertical axis is going to be gamma D is in kilonewton per meter cube, or grams per centimeter cube, or pound per foot cube, whatever is the unit we are following, depends. Okay, so when this test is repeated 5 times, so in the beginning we will see that the density is going to increase, and then later on this density is going to decrease. So if we combine these points, it is going to make a kind of bell shape. So once this bell shape is developed, then we can get what is the optimum water content and what is the maximum dry unit weight. So remember, this is for a standard Proctor test. When we give energy to the 3 layers, we place the soil in 3 layers, and to every layer we compact it 25 times with the standard hammer, whose weight is 5.5 pounds. Okay, let's look at it, how to calculate the water content. It's very simple. Let me just show you one simple calculation. Let's look at it. Suppose we take a soil, we take the soil and we put it in a can. So what is a can? Can is a small container, So it's a small container like this. It's a small container with the top cover. Okay, so that is what we call it, can. So we take a can. Let me say this is my can, and it has nothing in it. It's a dry can, and sometimes mostly we use a cover on top of it. Okay, so this is a can with cover. So if we are using can with cover, then use this cover in all the three cases. So this is can without anything in it. So let me call this is the weight of can. Then we bring soil and we put it in this can. Suppose we have a wet soil and we are going to put it in this can. So let's suppose this is that wet soil. So this is all that moist soil. So this is simply the can. This is can plus wet soil. Then we are going to place this can in the oven. Minimum is 24 hours. So if I look at the weight, let me call this weight as W, S and W. What is this S and W? Remember, because this soil is wet, so if I look at it, has three phases. What are those three phases? It has solid, it has water, and it has air. So it means the solids and water both have the weight, right? Weight of solid, weight of water. But whenever I write WCSW, it means it is weight of can plus solids plus water. Means weight of can plus wet soil. Then we put this in oven for minimum 24 hours, and after 24 hours, when it is in the oven and the temperature of the oven is above 100 degrees centigrade, mostly it is 110, close to 110. So all the water in it is going to evaporate. So the water, when it is going to evaporate, so what will be left here is only the solids. So this is going to be our can plus dry soil. Now if we look at the phase diagram, it has only two phases. What are those two phases? It has only solids and air. There is no water in it. So I can call this whole weight, if we do the weight, because the can is also there, so it is going to be the weight of can plus solid. So whenever you see this CS means can plus solid, CSW means cans, solid and water, and C is only the can. So suppose we did one test, and the can weight is, let's say it is 100 grams. We bring some soil with some water in it and we put it in the can and we do the weight again. Suppose this comes as 369.5 grams. And then we put it in oven for 24 hours, and after 24 hours we do the weight again, and this comes as 310.9 grams. Why it is reduced? Because water has evaporated. So how can we find out the water content? Remember, the formula for water content is weight of water divided by weight of solids, and we always express it as a percentage. Now, what is the weight of water? If you look at these three cases, so if you look at these three cases, the first one is the only can, the second one is can with wet soil, and third one is the can with dry soil. So you can look at these subscripts. So from there you can easily find out, how can I find out the weight of water. So let me call this is our 1, this is 2, and this is third case. So if I subtract this number 2 from 3, if I subtract number 2, this is number 2, and from 3, so you see CS. C is can, S is solids. Can and solids are going to subtract, so what will be left is the weight of water. So what is weight of water? It is W CSW plus, minus, not plus, minus, because we are subtracting, minus the weight of can plus solid. It is weight of can, solids, water, minus weight of can and solid. So what will happen? The weight of can is going to cancel out, the weight of solids is going to cancel out. What will be left is the weight of water. So this is going to be 369.5 minus 310.9. So this will give us 58.6 grams. So there was a 58.6 grams of water that has evaporated. How can I find out the weight of solids? It is very easy. Look at the last case, number 3. It is can plus solids. And then look at the first case. It is only can. So it means it is WCS minus WC. So you see, the weight of can is going to cancel out. Only will be left is the weight of solids. So this is going to be equal to 310.9 minus 100. So this should be equal to 210.9 grams. So let's now calculate the water content, which is weight of water divided by weight of solids. So when I put the values and I simplify, this comes as 27.8%. So this soil has a moisture content of 27.8%. So this is how we carry out the moisture content test in the lab. And this test is repeated minimum 5 times when we do this compaction test. Okay, so then let's look at here. If you look at this diagram, this bell-shaped curve shows us that the density is going to first increase, and then after the optimum water content it is going to decrease. So this is that optimum water content, and this is the maximum unit weight. So if you remember, we studied this in the chapter of phase relationship. Gamma D is GS gamma W over 1 plus E. You know this relationship. And also we studied this E is equal to WGS by S. So that E can be replaced here. So if we put this value and we place it here, so this equation is modified into this form. But if the soil is fully saturated, when the soil is 100% saturated, S is going to be equal to 1. In that case, the equation will be modified like this. So this is the equation for 100% saturation. 100% saturation means the soil is fully saturated, means there is no air in it. So when soil is fully saturated, it is a two-phase soil. It has only solid and water. It means it has zero air in it. Zero air. Okay, so this has zero air in it. So if I plot this ZAV means zero air void. There is no air in it. So that is called ZAV, zero air void. The gamma when there is no air in it, or I can say that when the soil is saturated. It is a saturated unit weight. So if we plot this, so GS is constant, gamma water is constant. So what is changing? It is only the water content. If we keep on putting the value of water content, let's say 5%, 10%, 15, 20, 25, and then we plot on this curve, what we are going to get is this curve. So this is the curve corresponding to 100% degree of saturation. So this curve has degree of saturation is 100%. Now in this equation, instead of 100% degree of saturation, we can say, okay, let's draw for 90%. So if we change, instead of 80 we do 90, or we do 80, we will get this curve, suppose. And then look, suppose this is for 60, and suppose this is for 40. So this is 80%, this is 60%, and this is 40%. So now we can easily see that in the beginning, when we are adding water content, so the degree of saturation is increasing, going from 40 to 60 to 80, and in the end this is going to, whenever we add water, there is no change in the degree of saturation. You see, now the degree of saturation is almost 80%, and we cannot touch this curve, and we cannot cross this curve, because if you cross this curve here, this degree of saturation will be more than 100%, which is not possible. So I think this is enough for today's class. We got some introduction about the compaction. So in the next lecture we are going to continue, and we are going to do some numerical problems. Thank you so much, and have a nice day.